Ever needed to estimate your steel beam or truss sizes in seconds without firing up your software? See, imagine fumbling through lots of tables. It's too slow. Today, I am going to give you steel design thumb rules that will save your time, make your work faster, and help you look like a pro in front of your seniors, even if you are just starting in structural engineering. See, these rules are adopted from the famous AISC rules of thumb articles by Leonis and Rudy, adjusted for IS 808 and BS steel sections, all in metric units. We will cover span by depth ratios, beam sizing, composite beams, column spacing, roof cantilever rules, truss weights, and even steel quantity per floor area. So let's first start with the depth ratios. Here I have listed out all the different categories. Let's say simply supported beam, continuous beam, roof trusses, floor trusses, plate girders, where depth is you can work out your depth based on span divided by particular number ratio. Let's take an example. Let's say for a 12 meter simply supported beam, the depth will be L by 24, and based on 12 meter span you can work out 0.5 meter as the depth of the section. Similarly, you can figure out the primary beam weight from your moment values. So for the structural steel which has a grade of let's say 250 megapascal, you can work out the weight based on the following equation. And here W is the approximate self weight of the section in kg per meter, M is your maximum bending moment in kN into meter, and D is the overall depth in mm. So let's understand this through an example. Let's say you have a span of 8 meter, UDL value of 20 kN per meter, M you can figure out using WL square by 8, which you are getting let's say 160 kN into meter based on the calculation. We assume the depth let's say 450 mm, and based on following equation, if you put the values you will get the weight as 178 kg per meter. So you can pick the nearest heavier ISMB or ISWB section. Now let's talk about the composite beams and shear studs. See, for typical composite beams, use 70 to 75% of the simple span moment for sizing. Let's take this through an example. So here is the shear stud estimates which is specified. You can check out this equation both for the working stress design as well as for the limit state design. Now let's understand for the column capacity what you can figure out. See, approximate axial capacity P can be figured out for let's say a grade of 250 material. P will be based on area into mm square with the following equation, where A is the cross-sectional area in mm square and KL by R is the slenderness ratio. We have all these equations for the different categories of the material. You can check out this. In the next phase, let's understand roof cantilever and splice locations. See, in case of a single story roof with the uniform load and equal spans, the economical roof cantilever length will be 15% of the main span. Similarly, end span will be 25% of the main span for the balance moment, and you can identify the splice location based on 15 to 25% span from the support where the bending moment is 0. So let's talk about the purlin spacing. See, for the purlin spacing, a quick guide is L by 8 to L by 10 for the span of the rafters. See, and for the truss depth, you can figure out the following equation where you can figure out the depth as span by 5. It is mostly economical for the most of the roof trusses. See, for the tension members, you can start with a section area of load into 100 mm square per kN. And for the compression members, use a slightly larger area to account for buckling. Now, the next turn is truss self-weight estimate. See, for the mild steel category where Fy is 250 megapascal, you can figure out the chord force using the following equation, which is displayed over here for the metric units, where D is the truss depth in meters. Similarly, you can figure out the chord area based on this F value that you have figured out earlier. So based on this, the total truss weight will be 3.5 times weight of one chord. Similarly, you can quickly identify the self-weight check for a particular segment. Let's say if you want to quickly check the beam's self-weight, a steel beam weights per meter is roughly depth in mm divided by 2. For example, a 300 mm deep I-beam will weight about 150 kg per meter. So this will help you quickly to estimate the dead loads before detailed design. Similarly, let's take another example. Let's say 500 mm deep beam. So its weight will be roughly around 250 kg per meter. The final number is for the steel quantity per floor area. See, for the braced steel building of let's say a grade of 345 megapascal, you can figure out self weight based on following equation. Let's say for the 6-story building, you can put this value in the equation and you can figure out rough weight per meter square. So I hope these equations help you out in figuring your primary section profiles and weights. See, these thumb rules are not a substitute for IS code design, but see, they are perfect for the quick estimate, sanity checks and early modeling. See, I have made a PDF. You can check out this particular cheat sheet for the metric units. Link is given in the description box. Thanks for watching. This is Chetan from the Civil Nirman, helping you master structure design the smartest way. So stay tuned for all the similar videos. Till then, I'll see you in the next video, and remember, don't just learn software, learn concepts.